Picture this, you're trying to make a network request. Let's say you're building the next big AI startup, but you don't have the funds and technical knowledge required for building your own large language model, and you shamelessly use the OpenAI API because that's what a normal developer would do. You give barely any attention to how the network request is made. Yes, you write the code, and I'm betting all the money I have, which is known, that you're making a fetch request inside of an async function. We are all used to the syntax of async/await or promises, but very rarely do we understand how this simple but powerful feature allows us to build non-blocking applications. One of the most satisfying parts of working with JavaScript is this ability to handle asynchronous tasks. While some of you might have a basic understanding of how asynchronous programming works in JavaScript, but on a deeper level, you fundamentally understand how JavaScript, which is inherently synchronous and will run on a single thread, executing code line by line, will allow you to write code that can be executed asynchronously. In today's video, I will take my time to explain in detail what asynchronous programming is and how it is implemented in JavaScript. So grab your favorite beer and let's ride, starting with the big fish in the room. No, not that fish. I mean this fish. Let's start with asynchronous programming. What the heck is asynchronous programming? Asynchronous programming is a technique that allows the program to execute tasks without blocking the main thread. Instead of waiting for a time-consuming task to complete, the program continues running other operations, and when that task finishes, its result is processed. This approach is essential for efficient input/output operations like network requests, file reading, and also for building scalable systems. Asynchronous programming in JavaScript is achieved via the use of the event loop, the callback, and the queue, and all of this is single-threaded by design. We have certain terms in that explanation we need to further split apart to understand more of what is happening, starting with threads. Let's look at threads. What are threads? A thread is the smallest unit of execution within the process. Hold on now, we've got another term, process, which we are going to discuss shortly, but for now, it is back to threads. A thread is a sequence of program instructions that can be managed independently by an operating system scheduler. This operating system scheduler is another term which I will also touch on shortly, but we are still on threads. Threads enable concurrent execution within a program, allowing multiple tasks to progress simultaneously. So now we have established what a thread is. Let's look at what a process is. A process is an independent instance of a running program with its own dedicated resources managed by the operating system. A process represents a program in execution, complete with code, data, memory space, and system state. Let's look at some key characteristics of processes. One process cannot access the memory of another process. The crash of one process does not affect other processes unless they are designed to communicate with each other. And a process can spawn a child process, just like how we can launch a terminal inside of VS Code. Each process has a process control block stored in kernel memory, and inside of that process control block we can find the process ID, which is the unique identifier for each process. We can find the program counter, which contains the next instruction to execute. We find the memory limits, which are code, data, and stack boundaries associated with that process. We see the open files and network connections that are related to that process, and last but not the least, we see the user or group privileges associated with that process. Threads and processes are fundamental units of execution managed by an operating system, but they serve different roles and interact in specific ways. So here is a clear breakdown of their relationship. A process is a container for resources like memory, files, CPU time, while threads are workers inside of the container that execute tasks. Each process has at least one thread, which is the main thread, and a process can spawn multiple threads to work concurrently. Threads share the process's resources like memory, files, but each thread runs independently with its own stack, and the stack contains local variables and function calls, a program counter, which is the next instruction to run, and a register state, which is the CPU context. We can think of a process as a factory with its own building, supplies, and budget, while threads are workers inside of that factory that share the factory's resources but performs separate tasks. So some key differences between processes and threads are: processes are heavyweight, that is, they are slow and they need operating system setup, while threads are lightweight, that is, they are fast and they can share existing resources. Processes are crash safe, that is, they fail independently. The failure of one process will not affect another process. why a single thread crash can kill an entire process. Processes are complex and require inter-process communication, IPC, while threads are simple with direct shared memory access. How do they interact with each other? There's a single-threaded process where one thread handles all the tasks just like a simple CLI tool. And in this situation, blocking one task blocks the entire process. There's a multi-threaded process where multiple threads run concurrently within one process. Example is a web browser where a particular thread might download image, a second thread might render the web page, and a third thread might handle user clicks, okay? And finally, there's a multi-process application with separate processes running independently, just like how Chrome uses multiple processes for tabs and they communicate with each other via IPC, just like how we identified earlier. And this IPC could be through pipes, sockets, or shared memory. So now we have established what a thread is and what a process is, and we have also seen the relationship between the both of them. Let's look at the operating system scheduler. The operating system scheduler is a core component of an operating system that decides which process/thread runs next on the CPU. It ensures efficient resource use, prevents starvation, and balances responsiveness across all tasks. Why do we need an OS scheduler? An OS scheduler is important for CPU utilization. It keeps the CPU busy and switches to a ready task when one is awaiting input/output. It prevents any single task from monopolizing the CPU's resources, and it maximizes the tasks completed per unit time. Each browser tab is typically its own process in modern browsers like Chrome, Edge, or Firefox, but a single tab can also use multiple processes for advanced isolation. Over the course of this video, we are going to assume that a browser tab is using a single process for its execution. JavaScript is fundamentally single-threaded, meaning it only uses one main thread for execution using the browser's tab process. This design simplifies programming but requires careful handling of blocking operations. Here is how synchronous execution works in relation to threads and processes. Each browser tab runs its own renderer process, and within this process, JavaScript executes on a single main thread. All tasks like DOM updates, event handling, and JavaScript code runs sequentially on this thread. JavaScript will execute code on this thread in sequence without interruption, and one operation must finish before the next one can start. Take a simple JavaScript program. The main thread runs console.log start first, then the main thread is blocked by the CPU intensive loop, and after 3 seconds, console.log end runs. During this time, the tab freezes up with no UI updates and no event handling. In order for JavaScript to behave asynchronously, there's an event loop which manages asynchronous operations like set timeouts, fetch without multi-threading. The event loop delegates I/O tasks to browser APIs which use background threads, then queues callbacks. JavaScript uses the browser's multi-threaded capabilities behind the scenes. Take a simple asynchronous code as an example. Set timeout is handled by a browser timer thread, which is outside of JavaScript's main thread. With the callback console.log timeout is queued in the callback queue after 0 milliseconds. The event loop moves it to the main thread only when the call stack is empty. Callback queue, the heap, the call stack, and the event loop. We are going to take a look at all of this shortly, but let's start with the callback queue, the heap, and the call stack. Since we have already established that every JavaScript program is a self-isolated process, and the process provides queue, which is a term we are going to look at shortly. Meanwhile, each thread has its own stack. Stack is another term which we are also going to look at. The heap is a largely unstructured area of memory allocated to all the threads currently running in a process. Let's think of the heap as an area where messengers on horseback wait before they get to deliver their messages. When it gets to the turn of a messenger, they unmount and move to the queue. In this area, they are attended to in a first in, first out manner, and when each messenger dispatches their message, there is usually a reaction to that message, which in our case is a function call. And for every message in that queue, there is a function associated with it. The function is called when the message is processed out of the queue. Each function call creates a stack frame that contains the statement and expression in the function. When that function returns a value or void, its frame is then popped out and the next function will begin executing. If we call a function inside another function, a frame is going to be created for each of them. The frame for the nested function sits on top of the frame for the function that called it. When the nested function is done executing, it will return and get popped off, and the main function will continue executing, and then it is going to return and get popped off. The items in a stack are treated in a last in, first out format. The stack is a data structure that holds the frame for each function. We can deduce that this is a synchronous process. So how is concurrency achieved with the stack and queue? Here comes the event loop. The event loop is simply a loop that iterates through the queue and processes any messages, if any, is inside. Since we are in a JavaScript development environment, messages could be added to the queue as a result of events happening in the DOM. The event loop does not really care where these messages arises from. Its job is to process the messages in the queue. It is interesting to remember that a stack frame, which is in essence a function call, can emit an event that adds a new message to the queue, or it can directly add a message to the queue. So when the result of an expression might take long, there are APIs that allow us to add that result as a message when it is available to the queue, so that we can go on processing other things without waiting. This is the basis of callback based code. This is also how set timeout and set interval adds messages asynchronously to the queue. When we write a set timeout function, a message is added to the queue after the specified delay in milliseconds. And from this example, when the first function is executed, a new stack frame is created. We create a variable and then use set timeout to call the function passed in as the second argument, and we give it the variable we created earlier. If the first function has to take some time before completing, the action would have to wait. But our code does not have to wait, and it moves on to processing the next statement. When the result is ready, action is called with that result passed in as argument to the function. A new stack frame is created for it, and the messages in the queue is processed if there are any. The above process is synchronous. The event loop is usually expressed in terms of a while loop. So to take advantage of the event loop, initially JavaScript used callback based code, then we got to promises, and finally we have async/await. Let's look at what callback-based code is and how it is used to achieve asynchronous programming. Callback-based code is usually the first solution to asynchronous programming, and it involves passing in a function as argument to another function. The function we pass in as argument will delay execution until the initial function has finished running. Then the function we passed in as a callback will run. Let's look at promises. Promises represent a cleaner way of performing asynchronous tasks. A promise will basically return the result of an asynchronous process, and you can access that using a then method to handle any data that is returned, or you can use a catch method to handle any errors that arise. Let's look at the basic syntax of a promise. A promise is declared using the promise constructor, and it takes a function as an argument. That function we pass as argument to the promise takes in two parameters, resolve and reject. We use resolve to return a value from the promise if everything is okay. Meanwhile, we call reject to return an error if something is wrong. The data that is resolved can be accessed using the then method, and it takes in an argument that represents the data that is resolved by the promise. In the example above, we just log it out to the console. We didn't handle failures, but if there were any failures, we use the reject parameter and reject a value with it. The data that is returned by the reject method is made available on the catch method. Now let's look at async/await. Async/await are a relatively new feature of JavaScript that makes handling asynchronous operations easier. We can mark a function to be asynchronous using the async keyword, and then we use the await keyword to await some asynchronous tasks and continue writing other logic inside of our function. Async/await are a much improved way of dealing with promises. When we use the async keyword to mark a function as asynchronous, it means that at some point we do some form of asynchronous work, and then inside the function we use the await keyword before the asynchronous operation, and in our case it is a network request function. This is what will happen. The function will start executing, and when it encounters the await keyword, it will suspend with the function and move on to the next thing. When the value from the network request is available, it continues with the async function and we see our data log out to the console. The await keyword simply waits for a promise to evaluate and return a value or an error so that we can continue with the rest of our code. So now that we have seen how asynchronous programming is achieved in JavaScript, let's look at some major takeaways from this video. We established that asynchronous programming is a technique that allows a program to execute a task without blocking the main thread. Asynchronous programming in JavaScript is achieved via the use of callbacks, the event loop, the call stack, and the callback queue. Threads are the smallest unit of execution within the process, and it's a sequence of programmed instructions that can be managed independently. A process is its own independent instance of a running program with its own dedicated resources. It represents a program in execution. The JavaScript code you write runs on a single thread, and asynchronous behavior can only be achieved using the event loop, the call stack, and the queue. You can continue building your next big AI startup, which will hopefully fail or get acquired for billions and billions of dollars by these mega tech corporations. Anyway, ensure you like the video. Don't forget to subscribe to the channel so you can get access to all of our videos in the future as they drop. And I'm going to see you in the next one.